Hello, everyone. Good night, good afternoon, or good morning. It doesn't matter whether you're brewing beer or brewing coffee, you're in for an excellent session today. So without any further ado, let's hand over to the chair of this session, Lucas Chiesa.
Hello, everybody, wherever you are. I'm Lucas Chiesa from Universidad Diego Portales in Santiago, Chile. And first of all, I would like to congratulate the organizers for putting together this very nice virtual conference. It seems that the combination of Zoom, Slack, and Slido is working very well. It is too bad that we cannot have all of you here in Chile to watch the eclipse next week. But on the other hand, I think that this format allows us to reach a very large audience. I see a lot of people connected today. So today we have 3 invited reviews, and it is my pleasure to introduce the first speaker, Paola Pinilla, and she will tell us everything about dust evolution and the formation of planetesimals. Paola tells me that she's losing her voice a little bit today, so the presentation will be slower than usual, but please, Paola, do take your time and we can move the Q&A to Slack if we need. So Paola, please go ahead.
Perfect. Do you see my presentation?
Yes.
Perfect. Okay, hello everybody. Thank you very much to the organizers for the invitation. All of you, thank you for tuning in, and for the ones that are gonna watch this later. Okay, I have the challenging task to summarize dust evolution and planetesimal formation in the next 45 minutes. Let's see how that goes. So I want to start with this figure from Shine and Udin in 2010, where you can see the processes that can help to grow from interstellar medium dust to planets. And in this arrow, you can see basically sizes, and observers usually use size, while theoreticians usually use the Stokes number. And in here, you can see that this was actually done for a few astronomical distance from the stars. So a particle of 1 meter size corresponds to Stokes number equal 1. But in the outer disk, when the disks are less dense, a particle with a Stokes number equal 1 corresponds to pebble size. And you can see that this is divided mainly in 2 processes. One that are called bottom-up process, and that means basically growing from interstellar medium dust to pebbles. And that involves all the dust evolution processes like coagulation, fragmentation, and includes several barriers, as I'm gonna explain in the next slides, like drift, bouncing, fragmentation. Then we have the top-down processes that basically help the dust particles or the pebbles to go up in this ladder that are called like top-down. And you can see 3 examples here of those processes. For instance, gravitational collapse triggered by turbulent clamping, gravitational instability assisted by drag, and one of the favorites, streaming instability. And once you have grown to basically planetesimal size, due to the accretion of planetesimals, we can grow planets. And we know that this picture is a bit old because we can also have pebble accretion to form planets. So my talk is divided basically in these 2, in first dust evolution and then planetesimal formation. So let's start with dust evolution. So basically in a disk, at time 0, whatever we call time 0, we expect that all grains are as the interstellar medium, so submicron sized particles. And these particles can feel or can move in the disk thanks to different mechanisms, including Brownian motion, turbulence, settling, and radial and azimuthal drift. And what is important here to say is that each of these processes depend on the grain size or the Stokes number. And when they are moving with this, with certain velocities in the disk, because of any of these transport mechanisms, they will collide. And when they collide, they will change the particle size. And therefore, modeling the transport of the grains and the collisions together is very important. This is basically like a marriage that you cannot break. So what is the possible outputs after collision? You can have is that the two particles meet and stick, or they bounce, or they transfer mass from one to each other, and this usually happens from the small particle to the large one. And you can have fragmentation or erosion. And what we do is that at a given distance from the star, we calculate the velocities due to all these transport mechanisms that I explained you before. And we set a threshold for the fragmentation velocities based mainly on laboratory experiments. And this is the kind of output you can get. So you can see in this plot, in the two-axis grain size. And this is calculated at 3 astronomical units from the star. You can see that very small particles, micron-sized grains, when they collide, they stick. And from micron to centimeter size, what we expect to have is sticking and bouncing. But the overall output is growth, and this is why it's in green. If we have collisions of particles with the same grain size of around 1 centimeter, what will happen is the particles will bounce. And it's in yellow here because this doesn't help to grow or to fragment. So we get stuck there, and this is called the bouncing barrier. One way to overcome this problem is that we insert a lucky particle in the disk that is slightly bigger than the rest. So we are in this or in this regime. And for that reason, we will have a mass transfer and then growth of the grains again. And at these distances, when particles reach like 1 meter size, the relative velocities are so large that we expect fragmentation or erosion. And these relative velocities come mainly from turbulence or drift. So let me explain you where the radial drift velocities come from. So this basically comes from the fact that the gas is a pressure-supported fluid, while the dust is not. And when we take the forces that act in a parcel of gas, we have the gravitational force, the pressure support, and the centrifugal force. And because of this term, the azimuthal velocity of the gas is not exactly Keplerian, but it depends on this second term that is proportional to the pressure gradient. And pressure is proportional to the density and to the temperature, and we expect both of them to decrease with radius. So this term is negative, and the gas will move sub-Keplerian. While the dust doesn't feel this pressure support, and therefore tries to move Keplerian. And something that is very interesting is that the difference between the gas velocity and the Keplerian speed basically will give us the hand wind that particles will feel and will make the particles to lose angular momentum and drift inwards. And this difference is proportional to the luminosity of the star, to the 1 to the 4. This proportionality is not so important, but then is also proportional to 1 over the root square of the stellar mass. And this is very interesting because it's telling us that the drift of the particles is more efficient around low mass stars. And as a consequence of that, we expect already that drift will leave a very different imprint in brown dwarf disk versus the Tauri disk, for example. And you can see this in this plot where I have that's radial velocity versus the grain size. Again, at 3 astronomical units. And we have 2 lines here, one for T Tauri disks And you can see that small grains are well coupled to the gas. They move with the gas. Once they grow and reach sizes of around 1 meter, or Stokes number equal 1, they reach the maximum drift velocities, which are of the order of around 2,500 centimeters per second. They are negative because they are toward the star. So if they meet with these velocities, they will probably fragment. And if they don't meet, they will drift very fast. If they can continue growing, they will decouple from the gas and they don't drift anymore. Now, the same kind of plot is here for a Browndorf disk. And you see the same behavior, it's only that these disks are less dense, so smaller particles decouple. And the velocities, the drift velocities are much higher because of this relation that I mentioned before. And they can be double amount. Okay, one of the very first models that included all this transport of the grains and the collisions is in the paper by Brouwer in 2008. And actually, I'm very proud to have access to this video that I'm going to show you. So you will see the evolution of the dust density as a function of grain size and distance from the star. And here, all the grains initially are micron-sized particles. You see they grow, and eventually, once they reach certain sizes, they are all drift toward the star. And at million-year timescales, we almost don't keep any pebbles in the disk. Now, these models have been significantly improved by Till Birstall, and you can find basically the results or the summary of these models in his paper of 2010. There are similar models by Sebastian Kraigt, and Sebastian Stamler and Till Birstall are working on a user-friendly code to make public in the next months or years. Okay, there is also a poster about dust evolution by Kimran. Okay, so what happened when we compare the results of these models with pre-ALMA data? So one of the observational diagnostics that we were using and we still use is the spectral index, which is basically the slope of the SED at millimeter wavelength. And this spectral index, when the emission is optically thin, tells us something about the grain size. And when the value is lower than 3, we can conclude that millimeter grains have growth in these disks. And you can see here a collection of the spectral indexes calculated between 1 and 3 millimeter versus the 1 millimeter flux. And this is here for 2 star-forming regions and different stellar types. And you can see that for all the disks, independent of how bright they are or around what star they are, they all have a spectral index lower than 3, meaning that somehow we can keep these grains independent of the drift that we expect. When we compare those models, these kind of models that I showed you before with these observations back in 2012, what we found is that models of radial drift, with radial drift basically, fail on explaining these low spectral indices. And in 2012, we took these dust evolution models and include pressure bumps radially distributed in the disk. And these pressure bumps came, in this particular case, from MHD simulations that show that these pressure bumps could have around 20% of amplitude with respect to the background density. And basically, this is the snapshot at 1 million years of evolution. You can see that in comparison with the previous simulation, we can keep millimeter grains. And we predict that if that is the case, we will expect concentric rings around the star. Now, this idea was new, and the idea of pressure bumps or dust traps. This actually came back. Okay, before I go back to the next slide, we also compared the results of these dust evolution models and predict what are the spectral indices. And in that case, we could explain these low values. But as I was saying, this idea wasn't really new. It was presented in the beautiful figure 1 of Whipple in 1972, where you can see that if you have a pressure bump, and in the region where you have a pressure gradient that is positive, you expect that the gas moves super Keplerian and particles will feel a tailwind and move outwards. While here, while they move inwards, as I explained you before, and in the pressure maximum, the gas moves Keplerian, and there is no anymore headwind or tailwind, and the gas remain there. So as a result, we basically accumulate particles there. In this, if the pressure bump is symmetric, then it will look like a ring. So when Laura asked us on Monday, how did I feel when I looked at the image of HL Tau, I think what I got was like happiness, because it is amazing to see that something that it was predicted almost 50 years ago was seen by ALMA in 2015. And since then, since the HL Tau images, we have learned so much about the structures. And we are gonna hear about structures in general tomorrow in Andrea's talk, but I'm gonna briefly summarize some of the main results that are very important in the context of dust evolution and planetesimal formation. Okay, one of the very common and one of the most obvious results is that structures are common in bright disks. And I want to emphasize here bright disks. We know that from the discharge sample that is targeting the brightest disk, we know, but also from the recent results from Odyssea that we're aiming to target the brightest disk in Ophiuchus with a resolution as good as the sharp or even a little bit better. And this was recently accepted and is in the archive. And Camilo and Lucas have a poster with these results. But in less basically biased samples, we find structures in around 30% of the disks. And this is based in the results from the Taulos observations at a resolution of 0.1 arcseconds. And interesting, we find that these structures are all in the extended disks. So the ones that are in the dust are more extended at 55 AU. Recently, Fang Long obtained 2 wavelength observations of a couple of these disks and compared the distribution at the 2 wavelengths to test the idea that these structures are due to particle trapping. And Feng has a talk in this conference about this. One of the other results is that structures also exist in class 0 and class 1, and we are going to hear about this tomorrow. And there are also a couple of talks about this kind of disks with showing structures, and one in particular that I want also to promote about models by Hugo. And what I found very interesting here is that if they try to explain these structures by planets, the planets that are needed are similar to the class 2 disks, which is a little bit puzzling. Okay, the other main conclusion that we have found is that transitional disks are very diverse. We talked, well, yesterday Barbara and Ilaria talked a little bit about transitional disks, and we had this idea that transitional disks have cavities and a ring-like structure around. And now we see that many of these rings are actually composed by more rings and gaps, or that some of them will have clear asymmetries that are mostly assumed to be vortices. There are also here 3 talks that I will recommend you to hear about vortices in disks. Some of them also show arcs, and I have two different basically asymmetries and arcs, because it's not clear if some of these arcs are or not vortices, like in this case, MW758. We also know that in some transitional disks, we observe shadows, in particular in the near infrared. And there is a talk by Rebecca Neal on trying to explain the origin of these asymmetries, but also how in some cases these asymmetries can be time variable. We also see spiral arms, mainly also in the scattered light, but in some cases in the millimeter emission. And something that I found very interesting is that in some of these transitional disks, now we observe an inner disk at the millimeter wavelength. And in most of these cases, I would say the majority, this inner disk remain unresolved. But it's very interesting why it exists in some and why not in others. And there is a talk by Logan Francis about the inner disk of transitional disk observed with ALMA. The last thing I want to talk about these structures is that we also see them around very low mass stars. And when I talk about very low mass stars, I refer to 0.1 to 0.2 solar masses. These disks are very faint and they are very small, so they are very difficult to observe. We need high resolution, but also high sensitivity. And recently, Nicholas Kortowicz has presented a small sample of 6 disks in Taurus. And you can see that in 3 of them, actually, we have structures, and in the other 3, we don't. And the ones that show structures are the more extended ones. Now, because these are so faint, finding structures like in this disk is very challenging in the image plane, and it becomes almost crucial to do it in the visibility plane. And here is where tools like Frankenstein and Galario are becoming essential. And I would say that in general, if you have data from ALMA, always look at your visibilities because there are so much information there. And I want here to promote the talk by Jeff Jennings and his poster also. We found in these particular disks that the gas extension, because we have 12CO and 13CO, is much more extended than the dust. And I think we found the largest difference observed so far, a factor of 6 in the case of C-7. And Nicholas has a talk here, and there is also a couple of talks about observations of this kind of disks. I want to promote also these 2 talks about models, and in particular, the talk by Dimitris, because we also here look at the planets that we need to form these cavities that we observe. And it results to be of few Jupiter masses, kind of Saturn mass, which is very, very challenging to form in this disk by core accretion. So the only remaining theory that we can have is gravitational instability. And Dimitris have a talk about this for this kind of disks. I think to test these models from observations, we need observations of young disks around very low mass stars to see if we see any signal of gravitational instability. Okay, so before I move to, again, back to the models, I have a poll about compact disks. So, because this is kind of the first sample that we have observations of very small disks around very low mass stars. And I wonder, what do you think we will observe when we have high angular resolution of a sample, a big sample of disks that are compact? Okay, we can see the results at the end. So before I move, I want to say here, thank you to all of you who have collected and have done a lot of efforts to get this data, but also to the theoreticians who have done also a lot of efforts to understand these structures. So the natural question here is, what is the origin of the diversity of these structures? And I'm gonna show you 2 slides that I think most of the people don't like, but it's basically the potential origins of the observed structures. And we can have zonal flows, and this is a relatively old idea from 2009 from Johansen. And it's the ones that I showed you before in the dust evolution models that I used in 2012. We can also have gradients of the disk viscosity. And there is a talk here by Timmy Delage, who has developed MHD code non-ideal MHD to see how the disk ionization can change the morphology of the disk. We can also have self-induced dust traps, secular gravitational instability, which is actually very particular because when many people saw the HL Tau image, they first thought about this before planets. And there is also talk about this in this conference. There is the idea of particle growth by condensation near the islands. And I think many of us have actually excluded this in the big surveys like D-Sharp or Taurus or for transitional disk, because we tend to say, oh, they don't coincide with the locations where we expect the islands of main volatiles. There are many effects that can change those locations. Some of them were mentioned by Anna on Tuesday, and I want here to promote also the idea that radial drift can also change those locations, right? There is a paper by Ilsa Clips in 2016, if I'm correct, where she shows that because we have radial drift, we can warm the regions where particles are not anymore present or they are depleted. And that will make, for instance, to have 2 CO islands in the disk. So now that imagine that you have a pressure trap by any reason, you also will move your islands due to the trapping of the grains, or maybe have more than one island of the same volatile. In any case, there are a couple also of posters here about this, one by Matthias Karate and one by Catherine Tross. We can also have magnetic disk winds and magnetically induced substructures. We can have sintering of those particles, of course, planet-disk interaction, and there are several talks and posters at this conference about this. Photoelectric instability, baroclinic instability, and dust settling, and viscous rings instability driven by dust. Sounds a lot, but it's the truth. And I want to say thank you to Stefano, who started this summary. And before that I forget, that there is also one that I have been forgetting to add, and is the interaction of the envelope with the disk. Now that we observe structures in class 0 and class 1, we should remember that one. There is a paper by Jeff Lesueur in 2015, and also some simulations by Stella Hoffner that show structures due to this interaction with the envelope. So given the long list of things that can basically form structures in disk, what is urgent and is very important is that we have predictions from these theories to compare with observations and be able to exclude or to know what is creating these structures. I'm gonna give you here an example of this kind of comparison that we can do. So you see here the dust density distribution in the case of a dead sun versus a planet. In this side of the slide, you see a dead sun that extends up to 20 AU. And in this case, we have a planet of 9 Jupiter mass at 20 AU. I'm not gonna go into details, but you already see by eye that these dust density distributions are very different from each other, even though we have trapping in both cases. And one main difference is that if you look at the small grains versus the millimeter grains, you expect in this case that the cavity is of the same size as the millimeter cavity. But in the case of the planet, you expect the cavity in small grains to be smaller than in millimeter grains. And this is indeed seen in the synthetic images of these models, where you see synthetic observations at short wavelength versus ALMA wavelengths. This is the case of the dead zone, and the white line represents how extended is the dead zone. You see cavities here in the two cases, which are of similar size. While in this case, you see that the cavity increases with wavelength. Can we test these models? We are now having enough data to test this idea. And there is this paper by Marion Villanave, who is also in this conference, but her talk is not about this, but Antonio mentioned this in his talk, where we collected 22 transitional disk image with ALMA sphere, and you can see basically the cavity size in scattered light versus the millimeter peak. The green is where the cavity is the same size. And you can see that around 1/3 of the sample is near this line, meaning that they are good candidates for dead zones and not so good candidates for planets. And the rest of the sample is good candidates for planets. And indeed, PDS-70 is somewhere here. I don't remember which is the point. Now, and all these structures, the structures that we see due to planets, well, we don't know, as I said before, but we are also looking at what kind of planets they are and how they compare with the exoplanets statistics. And this is a very nice figure from a paper by Bai in 2018, when you can see the exoplanets discovered in this typical planet mass semi-major axis plot. And you can see the ones that we infer from numerical simulations of the discrete structures. And most of them are in a region where we still don't have the capabilities to observe them, but some of them are actually possibly observed by direct imaging. So that's one of the questions one of the postdocs at the MPIA is trying to answer. If we look at the capabilities of a sphere, what are the detection limits compared to the planets that we expect from these numerical simulations? And this is basically what you see in this plot for all these disks. And what you see in color is the detection limits, depending on if we assume hot or warm or cold stars. So hot being represented by red and blue represented by cold. And in the points are the planet companions, the mass of the planet companions that are expected in these objects. Now you can see that the first 9 disks, in principle, could have been already detected by a sphere, but only one, PDS-70, has been observed. So it's very puzzling why. It's because our models are lacking something, or it's because we are neglecting something from observations. These limits also have include extinction of the planets. So it is an open question. This is, of course, part of the talk, the next talk. Tyne also have a talk with a beautiful possible new protoplanet. Antonio also mentioned some of these results. And there is, of course, the talk by Sebastian that Laura also mentioned in her talk on Monday. Before I move to a planetesimal formation, I want to mention something that has been very important for DAS evolution models in the last 5 years, and is actually new results from laboratory experiments. Because these experiments have shown that the fragmentation velocities that we assume in our simulations are much lower than we actually thought. So I actually borrowed this slide from Gerhard Born, and I think this is in the paper by them in 2019. What they measure in the laboratory is basically the surface energy. And this is directly proportional to the stickiness force. Now, before 5 years ago, all of these experiments are very challenging because they are trying to keep the same properties, or like pressure and densities, temperatures that protoplanetary disks have. They were limited to temperatures higher than 200 Kelvin. And what we were doing before was basically to extrapolate that this will continue being a constant value if we have lower temperatures. But in the last years, laboratory experiments were down to lower temperatures, and you can see that there is a large difference in this gamma value, which is directly affecting the fragmentation velocities that we assume. And they can be an order of magnitude or even lower than what we thought. And that has very important implications in our DAS evolution models, because as introduced in the paper by Till in 2012, I forgot here to put it, we have basically 2 limits, the drift limit and the fragmentation limit. And in a typical disk, basically the fragmentation limit dominates, so it limits the grain growth in the inner part of the disk, and then is the drift limit. Now, the fragmentation limit is proportional to this fragmentation velocity that we assume from laboratory experiments, and is to the value, to the square. So if we decrease the fragmentation velocities by 1 order of magnitude, we decrease this by 2 orders of magnitude. And to keep like grain sizes of like pebble size in the outer part of the disk, then we will need to decrease alpha by 2 orders of magnitude. Now, reducing alpha that much may have some problems in our models. First, if we think that viscous evolution is regulating the accretion rates, if that's the case, don't look at the poster of John and also the talks that we have this week, then we will have very low accretion rates. But in addition to that, if alpha is extremely low, the disk will be flatter than we are actually observing, not only with a sphere, but also with ALMA. And Marion has a paper of beautiful, a talk of beautiful edge on disks observed with ALMA, where you can see a little bit the vertical structure of the disk. So this cannot be this that, or the dust cannot be fully settled to the midplane. And even if these two arguments don't convince you, we see, in particular in the D-sharp sample, that where the rings are resolved, that they are not infinitely narrow, they actually have a width. And this alpha controls all the diffusion of the particles inside this trap. And if it's too low, all the grains will be infinitely narrow because they will be concentrated in the pressure maximum. So what we did was to disentangle these the 4 alphas that influence the gas evolution: the gas alpha viscosity, the radial diffusion, the vertical settling, and the turbulent velocity, to see if we have low fragmentation velocities, what combination of these parameters help to grow to pebbles and trap particles. And I'm going to show you just one case that work, and that is if we have alpha, the one that controls the settling, and also the one that controls the diffusion, equal to 10 to minus 3, while the turbulence is very low, 10 to minus 5. This is a nice result because also goes in agreement with the low turbulent levels that have been observed with ALMA. And there is also a talk here by Kevin showing these observational results for 6 disks. And also I want to promote here the talk by Joanna, where she has recently studied how fragmentation actually can be beneficial for planet formation in the case of pebble accretion. Okay, this is all for dust evolution. And now goes the most challenging part for me, which is planetesimal formation. And I want to start this with the iconic simulation by Anders Johansen in 2007, where they show basically that particles can accumulate in this kind of filaments thanks to the streaming instability. So I want to start with that, with the streaming instability and what is it? Okay, so this is to visualize what exactly is the streaming instability. So before I told you that in a pressure-supported gas disk, the dust feels continuously a hand wind. So imagine in that situation when you are biking, that you have hand wind, although you should move with constant velocity as a particle in the disk. One way to decrease that hand wind is either that you grow or that there are people surrounding you. So in that case, in this particular case of disk, that the particle increases in size, or that you collect dust, right? So when you collect dust or you grow, you reduce the drift, and in that way, you feel less hand wind. Now, the control parameters to trigger the streaming instability is the Stokes number and the dust-to-gas ratio. And there are talks and experts on this topic in this conference. There is a paper by Daniel Carrera, who has recently studied the streaming instability also in the presence of a very smooth pressure pump. There is also the talk by Jake Simon and the poster by Xiyan Xu. I'm going to present you one of the state-of-the-art simulations of the streaming instability by Rixin Lee. This simulation is done in Athena. It's a local sharing box. You will see in this side the movement of the gas, very turbulent. The red colors means upwards, the blue colors mean downwards, and in this part you will see the dust and the collection of this dust in filaments, and then the clamping of this dust, because they also have self-gravity that helps to these particles to clamp, or to these planetesimals to clamp. Now, these simulations are, to my knowledge, the ones with the highest resolution so far. And the resolution here is essential because they help to follow the clamping of these dust particles and to know how many clamps you form and if there is clamping or not. So you can see in this simulation here the accumulation of the dust in the filaments and the clamps. You see it better here in this plane. And they form hundreds of clamps in the simulations. And they have run this for several Stokes numbers and also dust-to-gas ratios. And they have new conditions for clamping by the streaming instability. And this is shown here, where you have here in the y-axis the dust-to-gas ratio, the y-axis the Stokes number. And in yellow here is the previous conditions by Carrera et al. In 2015 and by Yang et al. In 2017. Now you see that they are in agreement in general, but the new conditions by Rixin, Lin, and Andrew Udin really have a sharp transition here at a Stokes number of 0.01. Which is good news, because that means that you can form planetesimals with lower dust-to-gas ratios if you have particles that have a Stokes number of this size. That was one of the questions yesterday of how, in the discussion, how fast we form planetesimals. And this is really giving us some answers here. We need to do more modeling with dust, and including dust evolution and planetesimal formation with this kind of new conditions to know when planetesimals are forming. I want here to quote the words of Andrew Udin recently in a conference, where he says simply, these new conditions highlights the complexity of nonlinear streaming instability. Now, coming back to ALMA, there is observational support of a planetesimal formation in rings with ALMA. And this comes from the D-sharp observations. And there is a talk in this conference about this by Sebastian Stadler. This is work from done by him. Now, the D-sharp observations show us that the optical depth inside these rings is actually almost the same in all of these somehow. And they study one particular disk, one particular ring, the ring number 2 in HD 163296. And what way they did in these models is to put a pressure bump at that location, run dust evolution models with and without planetesimal formation, and check the optical depth as a function of time for the two kind of models. So you see in the dotted line, the models without planetesimal formation. You accumulate dust there, and your optical depth increases very fast. And actually, this may answer one of the questions yesterday in discussion, how fast we form planetesimals. You can see already that at 0.23, million years, you already start to see the difference because of planetesimal formation. Now, because due to planetesimal formation, you remove a lot of the dust mass into planetesimals. You decrease the optical depth. And at the edge of the disk, you have a value similar to what is observed. It's really amazing. Another observational support of planetesimal formation by the streaming instability comes from our own solar system. And this comes from observations of trans-Neptune binaries. And basically, these binaries can have two types of rotations. They can be prograde or retrograde. And just to give you an idea, if this is the orbit of the sun, the prograde movement is basically such that you have this rotation, then you have some inclination with respect to that vector. And retrograde is basically the opposite. You have the rotation in this direction. And you need a lot of observations to conclude something out, the prograde and retrograde movement of these objects in our solar system. And this was done using Hubble and collected in this paper by Grandi in 2019. And what you see here in the dashed line is the observations, and this is the cumulative number versus the binary inclination, where you can see that almost 80% of the objects have prograde rotation. And in the solid line is the prediction from the streaming instabilities, which is really, really good. And actually, this contradicts the prediction from dynamical capture models that result in more retrograde movements of these trans-Neptunian objects. Okay, the last couple of slides, and come back to ALMA and say that the best laboratory really to study planetesimals, here, sorry, my mistake, is debris disks. We already saw this beautiful collection of data from the recent survey led by Luca Matra. And from these observations, they can measure very well the width of the rings. We discussed a bit that too. And these debris disks seem to have rings that are much wider than the rings are observed in protoplanetary disks. And you can see that in this histogram that Sebastian Marino shared with me. And the protoplanetary disk sample includes the data from the Sharp, Taurus, and Odyssea. And I have here to say that some of these, in particular the Taurus ones, remain unresolved. But that will only imply that this will move towards this region, right, to the more narrow locations. So how that is possible, actually, if there is any connection with these rings and debris disks, how can be that they become so wide with the evolution of the disks? So Sebastian has been working on this with one student of him, Ella Miller. And what they have done is to take the dust evolution models from Stamler and Birstall, include planetesimal formation as as also in the paper by Sebastian Marino, include a bump, but in this case, the bump is moving inwards, basically to mimic planet migration. And they are looking how is the evolution of the dust, but at the same time, the evolution of the planetesimals. So here you see only the dust, and you see how the bump moves inwards. They are exploring a lot of parameters, the amplitude of the band, how fast migrates, etc. And here you can see the evolution of the dust in blue, yellow of the gas, dust to gas ratio, and in green you will see how planetesimals appear and what is the distribution of the planetesimals a long time of evolution. And you can see that is indeed the case that planetesimals have a very wide distribution, radial distribution, but the dust is concentrated in a narrow ring. So stay tuned for more results. And I think I'm gonna spend 1 minute more for the last slide, because we talk about in the very first day, connecting dust evolution, planetesimal formation with exoplanets statistics. And I want here to promote a work by Oliver Volka, where they are really trying to do this in a very consistent way. So they are taking dust evolution models using the 2POPI code by Thiel in 2012. They take a planetesimal formation criterion by Christian Lenz in 2019. Now they put this in a planet formation model, so in a population synthesis model. These are the models by Bern, the state-of-the-art simulations by Bern models summarized in this paper. And then they study what type of planets can be formed. And this is the kind of outputs they can get. And just to give you an idea, when they have a planetesimal distribution, that it was a power law, they had to make the power law very steep in order to create hot Jupiters. But in these new models, actually, with the dust evolution and planetesimal formation, they can form them. So have a look at the paper if you're interested. And with that, I want to go to my conclusions. So first of all, happy 5, actually 6 years to everybody. This has been an amazing time. We are very privileged. So we have discovered structures in different types of protoplanetary disk, and still questions remain. The one of the poll, I want to see the results. Several theoretical models predict substructures, and there is, I really think, an urgent need to produce observational diagnostics for such models. And planets are only one possibility, and we have to remain in mind that the detections remain very low. I also present you that the last years we have also changed our perspective of dust evolution thanks to the results of laboratory experiments. And if we combine the results of these laboratory experiments with models, they agree with the fact that the disk should have low turbulence. Now, current observations of RIT with ALMA support planetesimal formation inside rings, and also observations of our own solar system support the streaming instability. And current and future work is focused on connecting these two main observables, protoplanetary disk and exoplanets. And with that, I want to thank you, and I hope you could hear me during the talk. Thank you.
Hi, Paola. Yes, thank you very much. That was a great review of dust evolution and the first critical steps of planet formation. And I think that Alvaro now will go to the poll, right? To the results of the poll. Okay, so the question was, what do you think very high angular observations with ALMA of compact disk will show, right? And it seems that most people think that they will show structures that will be a little different and will be more diverse than the structures that we see in the bright disk. So do you agree with that?
Very interesting. Yeah, I don't know if we will see at all very smooth disks, if we will have like infinite resolution. So I will go for more like we will see structures of different nature.
Okay.
Yeah, we'll see. We will see.
I guess, yeah, we have to wait and see. I think there are several programs in the ALMA queue that are trying to answer this question. So I guess now we will go to the questions in Slido. There are a lot of questions, and the most popular one, and I think it's the best question in the conference so far, is kudos to Paola for keeping up on giving the talk without a voice. Well done. Yeah, so thank you very much for the effort. We do have a lot of questions about structures, substructures. So tomorrow we will have a session about substructures, but it seems that people already want to know about what you think about the substructures. So one of the questions is, can we consider the results that 30% of the disk show structure has a minimum? Because, for example, Chef Henning's code, I think this is the Frankenstein code, can identify previously undetected structures. So do you think there are more structures than what we actually see in the current data?
I think this is a very good question. I do think this is very likely a minimum because the resolution was not as good as the sharp, and it would be cool to just repeat this unbiased survey with the resolution, a very high resolution. And I think we will see more structures. So yes, and on top of that, if we look at the visibilities, as I suggest, and also as Jeff mentioned, we will see even more. I think what we just need is the confirmation from the image, because we shouldn't forget that the visibilities are still biased towards the model that we put, right? I remember before the high angular resolutions of observations of TW Hydra, we look at the visibilities and we thought, oh, it can have rings on gaps or it can have a sharp outer edge, and both of them worked, right? Well, to fit the visibilities. So yeah, for the confirmation of all these structures that we see in the visibilities, we need high angular resolution observations.
Okay, so another question related to substructures and the observation is, can dust migration via pressure bumps explain the narrow gaps we see in HL tau? Is that enough to explain the observation, just pressure bumps and dust migration?
Yes, I think so. I think also the fact that we, in HL tau in particular, see clear variations of the spectral index inside and outside these rings is a clear evidence that we do have variations of the grain size that is indirectly coming from like pressure bumps. What is the origin of this is unclear, but this kind of multi-wavelength observations that have been done with ALMA are very important for all of these disks with the structures to really confirm that is pressure bumps and trapping. So we look for the spectral index variations, but also we look, for instance, that the rings become narrower and longer wavelength because we trace larger grains, and therefore they should be narrower. And that's related with the talk that I recommend you to see from Fang Long.
Okay, so a very related question, but not just about HL tau, but more in general. So are planets and dust evolution enough to explain gaps and rings and the diversity that we see in the disk, or we need additional processes also to account for everything?
I think planets are such a nice solution because it's also, you can tune the values of the planet mass, the location, the viscosity, the aspect ratio of the disk, such that you produce whatever you want. You can produce rings, gaps, vortices. Yeah, you can lower the planet mass such that you don't have really a pressure bump, but more a traffic jump, and that create a smooth structure. So you can, I think you can do it, and that is actually in the D-sharp papers. We saw that in the paper by Shang, right? That they took the D-sharp sample and took models with planets, and they could explain all.
Okay, that's very interesting. So you think that planets are enough? That you don't need
are enough, but you know, it's also tricky because I think Earth mass planet can play the same role than a Neptune mass planet with different viscosities in the disk, and so it's tricky. Okay. It's also important to know when this planet form, if it formed very early in the disk or it formed very late. So that also is important. That's related with the talk by Michael Hammer.
Okay, so we also have several questions about collisions from the beginning of your talk. So does the sticking, etc., depends on the makeup and size of the dust particles and the composition, silicate, amorphous, carbon, the structure?
Mm-hmm. Yeah, so it depends on both, right? Because on one hand, the relative velocities of the grains depend on the particle size. So indirectly, the particle size is setting how fast they can move, and therefore if they can stick or not. Now, maybe this is important for clarification. These laboratory experiments that I showed you before are with water ice. And laboratory experiments have shown that indeed, whatever dominates the layer of the dust influence the potential sticking or not. So if we have, our old paradigm was that if we have silicates, they fragment more than water ice. And this is very intuitive because when we play with snowballs, it's very different than when we play with sand in the beach. But now it seems to be the opposite, that silicates are more sticky, or maybe if we are optimistic, ice and silicates stick similarly. Now, before we also started to understand from laboratory experiments that water ice sticks differently than CO ice, for example. And I don't know what is exactly the status now of this comparison, but we think that CO ice is less sticky than water ice. So it depends, of course, of the composition and grain size.
Okay, thank you very much. I think we have time for the one last question that is related to that, on how complete are the laboratory measurements regarding the outputs of collisions? Are we really sampling the complete parameter space? Probably not. So what is the status?
No, not yet. And if you remember that slide, I also show you that they are starting to decrease the temperature of these experiments, but they are still in the kind of high regime temperature when we talk about protoplanetary disks. So they are around 150, 180 Kelvin. There is still a need to explore colder temperatures. Maybe, we don't know, it keeps lowering this plot or increase again is unknown.
Okay, so thank you very much, Paola, again.
Thank you for all of you.
For the effort and answering all the questions. I think we can move the rest of the questions and the discussion to Slack. So now we have the second invited speaker of the day, Alice Zurlo, and she will tell us about young exoplanets and circumplanetary disks. Hi, Alice, how are you?
Hello. Hi. Hope you hear me well.
Yes.
Okay.
Please go ahead and share the screen.
Sure. All right. So you should see my slides now. All right. Hello, everybody. My name is Alice Zurlo, and I'm a professor at Universidad Diego Portales in Chile. And today we'll talk about young exoplanets and circumplanetary disks. But first let me thank the organizer for inviting me. I'm very happy to be here. And if you noticed, all this conference is mostly about disks. There were many talks about disks, and the only two talks about exoplanet is mine, and the other one was on Monday by Didier Queloz. So I'm really honored that I'm giving the other exoplanet talk together with the Nobel Prize winner. I feel kind of a pressure here, but I really hope you will enjoy my talk too. So my talk today will be complementary with the talk of DTS, in mostly focused, if you remember, on a planet detection method which are indirect, like the transits and radar velocity or microlensing. I will mostly focus today on the direct imaging technique. And if you remember, we saw a very similar plot here, where we have all the exoplanet population together, so all the planets discovered with different techniques, and we have here the planet mass versus the semi-major axis. And if you remember, in the DS plot, the direct imaging planets didn't show up because they are too far away. So this technique is mostly detecting planets which are very big. They are giant, massive, gaseous, and also they are located at the very outer part of planetary system from 10 AUs on. And also, I just want to mention that all these planets that we are seeing in this plot, they have very different ages. So with the direct imaging, we can really focus on very young systems. So we can really study the first stages of formation of planets. Remember, the other techniques, the other indirect techniques like the transits and the radial velocity are strongly biased by the activity of the central star. So they cannot really study very young system. They are mostly detecting old system of giga years. And the direct imaging is exactly the opposite, is trying to target very, very young planets, because at the very first stages of the formation of planets, they're still very hot, they are self-luminous, and we can detect their own photons. We can separate the photon from the planets and the photons from the stars. And there are also, of course, other advantages. You can see here, this is a very good example. It's the system of Beta Pictoris. Here you can see an image where we can see the planet B detected with the direct imaging, and also the giant debris disk that we can see around the star. And with this technique, we can have a complete characterization of the planet. You can see in this case, which is very favorable, because we have many years of observation of this system, and we covered almost all the complete orbit of the object. But in general, we can, with the direct imaging, retrieve astrometric points to then calculate the orbital parameters of the planets. And also, as you can see, we can extract the spectrum of the planet. And as in the audience, there are many of you are experts in disks. You may like that with this technique, we can also study the interaction in between the planets and the disks, because we have a complete picture of the system altogether. Of course, if I'm talking about direct imaging, I cannot really avoid showing this very nice video of the first multiplanetary system that we detected with the direct imaging technique. Is the system of HR 8799. It's a type star, which is very young, in between 40 and 140 mega years, and there are 4 giant planets orbiting around this star. So you can see this is a collection of almost 10 years of observations of this system. So you can see that the 4 planets are orbiting here around, and this is, I think, a very good laboratory for this technique, because we have 4 planets orbiting together. So we can study the dynamics of the system. This is a job that my student Pedro Nogueira is doing, is studying the interaction in between the planets and their orbits, and also he's studying the interaction in between the planets and the debris disk that you can see here. There is an ALMA image. And of course, this is very important because you can see this system of HR 8799 as a solar system analog, because we have, as in our solar system, of course, it is very scale, because the central star is very big, so it is rescale. It is much bigger than our solar system, but it has 4 giant gaseous planets, and also debris disk belt. And today I will talk about planet formation. So this is a very nice simulation of how we can imagine a planet that is forming. So here we have a look at a protoplanetary disk, so where the planets are forming, and we have a tiny planet there that is carving a ring or a cavity, as you like. And we expect to have very close to the planet that is forming a circumplanetary disk or CPD. And you may see that there are two streams of gas that are flowing from the outer part of the disk through the inner part of the disk, passing by the planet itself. So this is how we can imagine a very schematic picture of a planet which is still in formation. So we call these objects protoplanets, exactly as we call protostars, stars that are still accreting material. And if they're accreting material, we can expect some accretion indicators, as, for example, the emission lines of H-alpha or Paschen beta. Of course, we can detect also these objects with a near-infrared counterpart, so with direct imaging, and we can use also the interferometry. In this case, we are detecting the circumplanetary disk and not really the protoplanet itself. So here I show some of the instruments available at the moment and that we can use to detect and to characterize protoplanets. And also I will show during this talk some results made all by these instruments listed here. So here we have in theory how we can expect to have a protoplanet. So here we are looking at a disk in its own. We are sitting in the mid plane of the disk. You can see the protoplanet here and its circumplanetary disk. So I just mentioned that we can detect actually accretion and H-alpha and Paschen beta signal from the protoplanet, but it is not exactly at the surface of the protoplanet that we expect to have a shock. It is at the surface of the CPD. You can see here in this image, we may think that there is free fall gas, or almost in free fall velocity gas, that is coming from the outer part of the protoplanetary disk, and it's falling down onto the surface of the circumplanetary disk, and it is producing this shock that can then be detectable with the H-alpha or Paschen beta emission. And in fact, there was actually a first detection of a protoplanet. This is presented by Salum and collaborators in Nature in 2015, a protoplanet around the star LK calcium 15. So this was a very interesting news, because we didn't even expect, we didn't even know that objects that tiny as protoplanets were actually emitting signal in H-alpha. But this was the first detection of a planet emitting or still accreting material, so the first real protoplanet. But long story short, some years after, we had at least a couple of work that are presenting that this protoplanet candidate is actually a part of the disk, of the circumplanetary disk. So in this case, this claim is not really confirmed. We don't really know if the protoplanet is real. But I will tell you another story, pretty long story. I think Almost everybody knows this very famous system, the system around the star PDS 70. You can see here the spectacular image of the protoplanetary disk around this the star, and you can see here this is a sphere image where you can notice that there is a very wide cavity in this disk. And first, the very first time, it was the very first time that we detected a planet inside the cavity of a protoplanetary disk, which is exactly what everybody was expecting. We were trying to see or to detect the responsible of these features on the disk, like cavities, like rings, like spirals of the protoplanet. And we were expecting the planet itself, like carving exactly as in the simulation that we just saw. And in this case, we finally detected the responsible of the big cavity in this disk. Here, the detection of the first planet planet B, or on the star PDS 70. You can see here multiple epochs and multiple bands. These are results from SPHERE and also NACO together. So this is a very strong claim. And we calculated the mass for this planet to be from 5 to 10 Jupiter masses. So it is actually, yes, a giant planet. And the good news is that this planet B is also accreting. It is showing exactly as the first claim of protoplanet signal in H alpha. You can see here superimposed in blue. You can see the infrared, the sphere image, and exactly at the same location of the planet, there is also some emission in the H alpha. So we can think that this planet is actually a protoplanet. It is still accreting. This star is very young, is 5 mega years. And the story is not over yet. 1 year later, around the star PDS 70, with the instrument MUSE installed at the Very Large Telescope, they redetect the signal coming from the planet B, but also they detected a second planet C around this system. So this makes this system the second multiplanetary system after HRT 799 detected with the direct imaging technique. And also, of course, it is a very, very interesting system because it has 2 protoplanets orbiting around the star and also inside the cavity of the protoplanetary disk. So it is super interesting. But still, as I told you before, it is a very long story. So as we saw, if we expect H alpha signal or a very high temperature and the shock produced, we also expect to have a circumplanetary disk around this planet. And in fact, studying the symphony spectrum here, as you can see, there is a clear mismatch in the near infrared part. So we can say that there is a near infrared excess in the spectrum of this planet. So we can think that this is an indirect way to say that there is a circumplanetary disk around the planet B, which is again expected. And also, I saw that there is a contributed talk by Jens Kammerer, who is presenting some result by gravity about the same planet and about the CPD. So I really strongly encourage you to say his contributing talk. And just to end the story of PDS 70, of course, you may expect that if there is a CPD around the planet, we can actually detect it with the interferometry, so with ALMA. And these are images from from ALMA, presented by Isella and collaborators. And actually, as you can see here, the disk is very clear. The signal of this is super clear. You can see the cavity inside the disk, and you can see there is some signal. You can see here a PSF inside the cavity. So some material there, some dust in the cavity of the disk. But the strange thing is that if we superimpose the ALMA signal at the near infrared signal, the signal from the dust is actually not at the same location at the planet. So this is not expected. We don't actually know why there is this mismatch. Maybe as we saw in the simulation, this is just part of the streams that are passing from the outer part to the inner part of the disk, but it is just a speculation. We don't know. So we expect that if there is a CPD, it should be located at the same location of the planet. So this is kind of strange. And I just wanted to briefly mention another very interesting system, the system around AB Auriga. So this is very spectacular, as you can see in these images from Sphere. This has been presented this year by Anthony Boccaletti, and you can see that there are many spirals, and there are many spiral features in these protoplanetary disks, and there are two features here that we can may think that are two protoplanets still forming, and that they are the responsible of the spirals of that we can see around this system. So this is a claim that has to be confirmed. It can be the interaction with these two protoplanets, but it also can be the interaction with a binary star. So we still don't know if these two features are actually real. I think it would be very interesting to see if there is any accretion signal, like the emission of H alpha or Paschen beta at the location of the two protoplanets. But this is another very interesting system to study. And still, of course, this system that I just presented are motivating a protoplanet hunting. So you can see here a gallery, and it's very tiny. We know that there are many other protoplanetary disks that are showing all these planet formation indicator. As I already told you, rings or spirals or cavity gaps. So we have many disks with these features, but still we don't know how these features are produced, and if the planets are producing these features. So this year I presented a survey, the biggest survey, to look for protoplanets. We selected all the protoplanetary disks that are showing this planet formation indicator, gaps, spirals, rings, etc. We selected just the closest system, as you can see here in this list, and we followed them up with the instrument Sphere in the visible light, and of course we try to look for any H alpha emission signal. And unfortunately, this survey detected no new planets, new companions. So far, the only strong detection of protoplanets, I think, are the two planets around the star PDS 70. But I think there are so many disks that have structures like that we should really keep continuing and try to study them all to look for the responsible of the feature, and to see if actually the features are produced by planets. And remember that these kind of surveys with the H-alpha should be more efficient than the near-infrared, because they're not really connected to the mass of the planet, but with the accretion rate of the planet. So in principle, we can also detect tiny planets, Jupiter mass planets, if they are strongly accreting. It's not like in the near infrared that we can just target very massive planets. So in principle, it should be more efficient. So I think it is a very promising way to look for protoplanets and to look for the responsible of these features. And also, I saw there are a couple of contributed talks on this topic by Curie and Bolas. So I really strongly encourage you to look at these talks. And now in this last part of the talk, I just wanted to present how I see the future, the present, but especially the future of this topic, how we study and characterize very young planets, protoplanets, and circumplanetary disks. So as I see the future, we will not only detect circumplanetary disks, but also satellites around the exoplanets that we already discovered. So I will just mention 3 techniques. There are many more, but I will just present these for the moment. The first, of course, is the direct imaging. So this is a work that my student, Cecilia Razzoni, has done. It is a very good work on implementing ad hoc routines to subtract the PSF of the direct imaging companion. So what we wanted to see here in the direct imaging archive that we have, if we can subtract the contribution of the companion, not the star, of the planet or the brown dwarf that we detected, and to see if there is any feature around the planet itself. The feature may be or an exosatellite or a circumplanetary disk. So this routine have been tested on first synthetic data, and then they have been tested systematically on all the direct imaging companions detected with the survey of sphere, the SHINE survey, the survey that we have in the GTO of sphere to detect the companions. Of course, the idea here is that to use the systematic study to all the direct imaging data. So we all know that the array is full of data of direct imaging companions, and so I think that we should apply these routines to subtract, to try to attenuate the signal of the companion itself and see if there is anything around the companion. So here you can see this is a simulation, how we can predict the signal of a moon or an exosatellite around the companion. So these are real data. This is one of the companions of HRT 799, and we injected a synthetic moon around the planet. So you can see here, this is the data with the synthetic moon. This is the model of the PSF that we want to subtract, and the residual where a moon can show up. So it is really depending, as you can see here, from the contrast, the flux difference in between the planet and the companion. But in principle, we are able to retrieve signal from an exosatellite if it is bright enough. And I just want to mention a couple of results that we had from this technique. The first is not a circumplanetary disk. It is a circumstellar disk, but it is around a bound companion. This is the system of JQ Lupi. This star, the star C, it is a very tiny star orbiting around JQ Lupi. And you can see that using this method, we actually discovered that there is a circumstellar disk, a tiny circumstellar disk around this small star. You can see here exactly the same technique where we subtracted a model of the PSF of the instrument, and the disk is showing up. And we know also try to model the disk to see some property of the disk itself. So this is one of the successful results that we had using this technique. And the second one, which is really promising, is the interesting system of DH Tauri. So this is a companion which is at the boundary in between planetary mass and the brown dwarf. It is at the limit of being a planet. It's around 12 Jupiter masses. And you can see here that in two different epochs, we retrieved some signal, a blob here, a PSF here, in the north of the companion DH Tauri B. So this companion is a planet of 1 Jupiter mass, if it's real. So this system is very exotic because it is a star with 2 planets orbiting around. So it's not really an exosatellite, it's kind of a binary planetary system that is bound to another star. So it is very challenging. If it's real, it is very challenging for the planet formation theory to explain how such a system can exist. So for this system, this is for the moment a claim. We have to confirm this. So we asked for JWST time to have another epoch of this system and confirm this detection of exosatellite. Of course, in the future, the best instruments to do and to use this technique are, as I just mentioned, JWST, because of the stability of the PSF. As you may understand, if we are trying to subtract the signal of the planet, we really need a good model of the PSF, and the PSF of the instrument should be stable over time. So JWST will be perfect to perform this kind of technique. And of course, in the future, the ELT, or in general the extremely giant telescope, will permit such a high contrast that we will be able to detect exomoons of the mass of the Earth. And this is very interesting, and is connected with habitability. So I know you didn't expect to hear about habitability in a talk about very young and super hot and gaseous planets, but exactly as in our solar system, we can maybe find some habitable zone in the moons and the satellites around our giant planets, even very far from the star, because there are other source of heating, like it can be the tidal heating, or like in the moons around Jupiter and Saturn, we can expect to have giant oceans with life, even very far from the star. So I think this technique and the look for exosatellite, it is very important for the future, even to look for life. The second technique that we present is mostly focused on the hunting of exosatellites, and it's called spectroastrometry. This will be possible with, for example, the iFuse mounted on extremely large telescope, as it can be Harmony, for example, installed in the ELT. So here we have a system of a giant planet with a moon that can be a telluric satellite. And of course, the system is not resolved, but we can observe the planet with an IFU. So what we expect, if there is the presence of a moon or of a satellite, that we have a tiny shift in the channels of the IFS of the center of the light. So the center of the light will be, as you can see here, it will be centered at the location of the planet when in all the wavelength where the planet is dominant. So the spectrum of the planet is stronger. But when in all the wavelength and all the channels where the moon spectrum is dominant, so you expect a tiny shift of the center of the light of the system. So this is an example where the central planet is Jovian type, and the moon is with a spectrum very similar to the one of the Earth. But you can see here that this tiny shift is measurable, and this is an indirect way to detect exomoons. And the last technique that I will present, of course, it is the interferometry. So in the audience, there are many experts on ALMA. And here, of course, we are trying to detect the CPD. As I mentioned before, not really the planet, but we're trying to look for a disk around an exoplanet. So here I present a very promising target. This is a brown dwarf around the star HC 206893. And this brown dwarf is very peculiar because it has a very strong near-infrared excess. So what we thought it was the presence of a CPD around, yes, it's a brown dwarf, but I will call it CPD anyway, a CPD around this companion. So we tried, you can see here the result of the ALMA detection. We don't retrieve any signal at the location of the brown dwarf. Maybe this the sensitivity of the instrument, we don't know, so we cannot confirm the presence of this CPD. And I know there have been many attempts also with other objects, other companions. For example, even they try to retrieve some signal on the star DH Tauri to see if the companion B was actually emitting some signal at this position, but so far we don't have any detection of a CPD around a companion. But the simulation that you can see here, they are very promising. So these are the expected, what we expect to see with observation in band 9. So this is a work by Judith Zulagi. So they propose to use the band 9 of ALMA because it should be the best way of detecting circumplanetary disks. So in the 4 panels here, the only difference is the central mass of the planet, and you can see that the circumplanetary disk looks very bright. It looks even brighter than the circumstellar disk itself. So we expect very high temperatures at the location of the CPD, and this is the reason why we should go for band 9. So these simulations are very promising, but still, as I just mentioned, we didn't have any detection of a CPD of a companion. But I just wanted to mention that we had a clear detection of a CPD around the free floating planet. So the only difference is not a companion, it's not bound, but you can see here, this is the planet OTS-44. It is a planet from 6 to 17 Jupiter masses, so in the boundary of brown dwarf, and it was actually showing Paschen beta emission as expected and near infrared excess. And actually, they detected some signal. It is very clear here that we are looking at a CPD, but is around a free floating planet. So I think we should try again because this is indeed possible to retrieve signal from a CPD. So this is a direct detection of a CPD, but there is another way of using the interferometry technique to detect, to not directly detect, but indirectly detect the presence of a CPD. And this is studying the effect on the gas kinematics. So you can see here, these are simulations presented by Seba Perez back in 2015. So you can see that we expect, here the zoom, we expect a deviation of the kinematics of the gas at the location of the CPD. So here you can see how the gas is interacting with the presence of a CPD. So if we have a kink on the gas, this is the 12CO, we expect the presence of a CPD at that location. So these are just simulation, but here we have the detection. So the simulation were actually right. The first detection here is around the star HD 1632-196. So it is pretty faint, but you can see here where the circles are, that there is a sort of deviation, the same kink exactly as in the simulation that I just showed. So we can expect to have a tiny CPD at the location. So you can see that here there is a clear asymmetry in between the two parts of the disk. And this is even more spectacular. This is the system around the star HD 97048. And here it is very clear the presence of the kink in the gas kinematics. And this is more spectacular because the position, the exact location where the kink is actually here. You can see the continuum image, and it is located actually in the ring of this protoplanetary disk. So it is exactly as we expect the planet to be. So this is very good news. Again, we are finding the responsible of the feature of the disk, and it is a planet again. So to conclude, I showed you that the high contrast imaging of exoplanets is a very nice technique where you can have a complete study of very young gas giants with separation, and it can have also the study of the interaction of the planets with the disk. And in the last year, we even have been able to detect planets that are still accreting, the protoplanets. And especially in the future, this technique with others, like the interferometry or the spectroastrometry, will permit the detection not only of planets, but also features around planets, as they can be the circumplanetary disks or even exosatellites to find life even outside our solar system. Thank you very much. I will take questions.
Hi, Alice. So thank you very much. That was a great review on a very hot and exciting topic. We do have a lot of questions here in the Slido. So let's see. There are several questions about the reality of these protoplanets, right? So the first question is a little controversial, I suppose. So in your opinion, how many of the young planet candidates that have been published are actually real? How many are not? Probably which one?
Well, yeah, this is a very good question. So I presented very few systems, and for these at least, I'm pretty sure that they are real. So there are many systems that we follow up and we observe with many different instruments, and also we have a lot of epochs, so we can actually follow up. We can even retrieve some orbits from these companions. So at least for all of them that have so many information, the spectrum, the orbital characterization, I think they are real. So and in some cases it's very hard to not be sure that they are not disk features. For example, in the case of HR 8799, there are absolutely no doubt that they are planets, and we have a lot of information. We have 20 years of observations of the system. So for some objects, for sure, we have so many follow-ups that we're pretty sure they exist. Of course, there are also systems like the first detection of the protoplanet LK calcium 15. There it is very hard to disentangle the signal from the planets and the signal of the disk, especially when we have systems like that where the planets are very close to the disk. It is very hard to disentangle. But I think at least for most of them, for most the direct imaging detection, we are pretty sure that they are real. What we don't know, what it's really difficult to say, is their mass. So there are many of them are in the boundary. They can be planets, they can be brown dwarf. So this is very difficult. As you know, the mass is absolutely model dependent. We don't have, at least not for all of them. For beta peak we have, but we don't have the information, the dynamical mass for of the planet. So when for favorable cases like beta peak that we have also astrometric information, we can retrieve the mass, but for others we don't. So this can be something that is with large error bars, not super sure, but the existence of these planets, I think it's pretty sure.
Okay, so we have another question about lead calcium 15b. So if it's not a planet, so what is the origin of the H-alpha emission that was detected?
This is a super good question. Yeah, so it is very hard to say why we have H-alpha emission from the disk. So in principle, this protoplanet should be the surface, the very first part of the disk, which is touching the cavity, the board, the edge of the disks. So we should not expect H-alpha signal. I don't know how in that position there are 10,000 kelvins, 20,000 kelvins. I don't have a clear answer. It is already hard to explain why we're having a H-alpha signal on protoplanets. We are trying to explain this with the presence of and the shock, as I showed, onto the surface of the circumplanetary disk. But in the case of the non-detection, I don't know. It's hard to say. It's hard to explain.
Okay, so there are some questions about how common are planets like PDS, those of PDS 70, and whether we have some statistics on that. So do you know how many targets with similar cavities have been observed with the same sensitivity and resolution? We can say something about how common they are.
So yeah, of course, we have many targets where there is a clear presence of the circumplanetary disks, and of course, all the disks that are presenting the features, we are trying to look for the responsible. So, for example, HL tau itself, it has been observed, and they have strong constraint on the planets that should be there, producing the rings, but no detection so far. So there are many systems that we follow up with the direct imaging technique, and for most of them we have very strong upper limits on the mass, and we're saying that maybe the structure can be also produced by very tiny planets, and if the mass is below 1 Jupiter mass, it is very hard to detect them with direct imaging technique. Of course, in general, as you may know, the direct imaging technique has not so many detections. So these planets at very wide orbits are not so frequent. So again, the frequencies of the planets that we detect is not very high. And yes, there are many statistics. You can check all the publication for all the surveys, the GPI survey, the SPHERE survey, and others. So there are many statistics that we may collect with the detection and the non-detection that we had so far. But yeah, hopefully we will find other systems as PDS 70. Which was the really first clear detection of two planets inside a cavity. But it's hard. It was a very favorable case because it's very young, so the planets are still very luminous and very bright.
Okay, so a question related to that is whether we are detecting this particular system because it's very young or because of the heavy accretion, and whether we can learn something about the time scale of the planet formation process, the accretion of the envelope, right, from this one detection.
So yeah, as I mentioned, we're talking about two different techniques. So for the near infrared, of course, the age of the system is key, because the luminosity of the planet is changing dramatically for all planets. So the planet is cooling down, and if you try to detect signal for very old planets, they are too cold, and they're not self-luminous anymore. So the younger the planet, the better, because at the very first year the entropy in the planet is very high. So you expect them to be very bright. So yes, in this case, this planet, which has just 5 meg years, it is really favorable because it is still very, very luminous. And in the case of the accretion, this is a complete different story. So even if PDS 70b was a tiny planet, but it was strongly accreting, it would be visible still with the technique in H-alpha emission. So the H-alpha emission is not related to what we are measuring here. What we are seeing here is not really the mass, but is the accretion rate, the mass accretion rate of the planet. So we're talking about two different things.
Okay, great. So we have now a couple of questions about the near future. In particular, what tracers, near infrared continuum, H-alpha, CO kinematics, or millimeter continuum, all the different techniques that you mentioned, will produce more discoveries in the near future, discoveries of protoplanets? What can we expect to see?
Well,
in the
I
coming year?
propose many techniques, many different techniques, because we should use them all. I don't know which one is the most promising. There are many techniques. I just mentioned few of them. Of course, for example, the technique of the spectroastrometry is very hard. It is very hard to get signal. Maybe, yes, we need very favorable cases, and it will be hard to perform. But of course, with interferometry, I think we already have many nice results, as I showed, of presence of CPDs. We have already a clear detection of a CPD, but around the free floating planet. So I think for sure ALMA is very promising, and it is immediately available. So I think we should have many systematic studies to try to detect or indirectly detect the presence of CPDs. And of course, with the new instruments, with JWST and with the ELT, but here we are talking about the near future, these two instruments will be key for this technique. So of course, I think we both, and also together, we can couple the two techniques together. They will be absolutely promising to find many more CPDs, and hopefully even exo satellites. And with this instrument, we also can target planets that are less massive than the ones that we target so far with the current instrumentation.
Okay, so there is another related question about Gaia. So planets' mass can be constrained through the astrometry motion of the host star. So can we do this for these very young systems that are typically embedded, or they are just too faint for Gaia to
so it depends. For example, yeah, with the case of Beta Peak, it was successful, but again, this is a very particular system, and we have many observation of these systems. In general, I think, yeah, many of all these protoplanets and young stars are embedded, so this can be a problem for Gaia. Faint, not all of them. So there are many objects that are not faint, but here for sure we need a wide range. So we need many observation, many years of observation. So we would need some years to have dynamical constraint, astrometrical constraint from the primary. So Gaia, yes, it would be absolutely important to couple with other techniques, but it will take years probably. So for the astrometry, we have to wait. We need a wide baseline to have some information for these planets, especially if they are small. Okay. And also many of these stars are very massive. We are talking about A-type stars, so we don't expect clear motion, astrometric motion of them.
Okay, great. Thank you very much. So we have a couple of questions from people probably observing proposals. So they want to know at which wavelength we can observe the CPDs using interferometry. What's kind of the best wavelength?
So from the simulation, as I mentioned, band 9 should be the best. For my proposal, I think I asked for band 7, but there it really depends. So there are many ingredients there that we don't know. So it's really a prediction. So I don't really know the answer. So from the simulation, it should be benign, but it really depends from the temperature of the CPD, which we don't have a clear answer. We don't know for sure which is the expected temperature of the CPD.
Okay, so we have a similar question from the optical and the near infrared. So they are asking, is H alpha superior for detecting accretion that bracket gamma, for instance?
So for that, I don't know. My personal opinion. So for the example of PDS 70, so with sphere we have the possibility of trying to detect this planet with the H alpha and also with the bracket gamma, because they are both available. And actually we didn't detect the planet with neither of them, so I don't have a comparison of which is the difference in flux and which is the contrast in between the H alpha and Paschen beta or bracket gamma. And as far as I know, there is no simultaneous detection of both lines together, because there are one in the near infrared and one in the optical. So we don't have still a detection, so we don't have a comparison. And I don't know. Actually, normally I always propose for both of them, but still we don't have a clear detection in the imaging. Always with spectroscopy, yes, but in the imaging, we never detect any protoplanet with other filters that are not the H alpha filter. I think we should try. Maybe it's better to go for the near infrared. It really depends from the instrument. For example, for sphere, the filter is not the best to use. So in principle, it's better to use the H alpha, but it depends from the instrument that you are using.
Okay, great. Thank you very much, Alice. I think that's all the time we have. We have to move the rest of the questions and the discussion to Slack. So thank again, Alice and Paola, for great presentations. I'm the only one applauding for everybody. So
thank you.
And I think we have a break now, a 30-minute break, and then we come back for the last talk of the day. Antonio, back to you.
Thank you. Thank you very much, Luca. Thank you very much, Luca. We'll take a 30-minute break now, and please take a moment to answer the poll.
Okay, great. I think, yes, we are hearing your dog. That's okay.
Hi, everyone. Welcome back from the break. We had an excellent session this morning, and we have one more very good talk coming along. On the meantime, while we wait people to come back, let's review the overwhelming results from the poll. It may sound like we put this as a loaded question to see ALMA shine, but it's really surprising to see that there seems to be a general consensus that ALMA has done fantastic in terms of revolutioning our understanding of planet formation. So without any further ado, I hand over to you, Lucas.
Hello, so welcome back. Yes, so I'm not surprised by the results of the poll. I actually agree with the results, but I should say that this audience might be a little biased, right? But yeah, so Alma is doing great. There is no question about that. So let's see. Today we have the last review talk by Nicolas Cuello, and he will talk about disk in multiple systems. Go ahead.
Okay, thank you. All right, let's share my screen. All right, so hi everybody. It's a great pleasure to be here today to talk about disks in multiple stellar systems. This is going to be a sort of journey into the realm of multiplicity. So my name is Nicolas Cuello. I'm currently a Marie Curie Fellow at the IPAG in Grenoble. And so the itinerary for today is going to be like this. So let me just move this over here. Okay. So we will first start with a bit of context. Why should we care about multiplicity? Then we're going to talk about disk flavors in multiple stellar systems. And then we're going to do a multiplicity tour. And we're going to see a lot of observations that happened in the recent years. And finally, we will draw some conclusions. But before we start, I would like to thank the LOC and the SOC for organizing such a great conference, and in particular Alvaro and Enrique, who did an excellent job in keeping this thing virtual and going, and all the HL towers gathered around the world, because we're all here and at a very low CO2 cost, which I think is something very nice. And without further ado, I need to acknowledge all my collaborators here, which did an excellent job also in the last years. And now let's start this. So why should we care about multiplicity? So we know that multiplicity evolves over time. And we know this because by doing surveys of regions of star formation, and in particularly targeting young stellar objects, we can count the number of multiple systems in these regions. And when you do that, you can define the multiplicity fraction, which is basically you take all the stars and you subtract from that sample all the stars that have exactly one young stellar object or one star. By doing so, what you're doing is basically adding the fraction of binaries, of triples, of quadruples, and so on. And you can show, given how the universe is done, that this is very close to adding the number of binaries, triples, and quadruples divided by the total sum, so single binaries, triples, and quadruples. And as you can see, so you can put some points in there, and we see that the multiplicity evolves over time and it decays over time, which means that young grids are likely multiple, and as they age, they become lone stars. But what's very interesting is that if you take a young stellar object between class 0 and class 1, the probability is fairly high to be multiple. It's between 40 and 70%. And then, for example, here, this is what D sharp observed, so class 2 stars. And what we can see is that since the WOW event, HL tau observation, we're moving towards observation of class 1 objects. And even in the last years, we're even going deeper, and we're doing the search of deeply embedded protostars with structure. And the search is very prolific, and we're going to see some very exciting results. Okay, so multiplicity, it's a byproduct of stellar formation. This is something that was shown very well by Matthew Bate through simulations. So you basically, what you do is you take a cloud and you let it collapse, and you study how stars form in this cloud. And when you do that and you follow the way stars form and the way material is accreted onto these young stars, this is basically what you see. You see that there is an enormous diversity of disks, and you see a lot of dynamical interactions, and especially you see misaligned accretion that happens for very long. I mean, here we're talking about 100,000 years at very most, but you see that it's a very chaotic environment and many things happen. So we're very far from this view of stellar formation as in an isolation that we often use in the models. So we come to this idea that all stars are born as binaries or multiples. This was proposed by Larson in the 70s. And one interesting corollary to this is that most, if not all, single stars were once part of multiple stellar systems. So that means that when you observe one main sequence star with a planet, let's say, after a few giga years, that means that perhaps in the past, when it was a young stellar object, it was part of a multiple. So one of the most important questions we have at the moment is we need to understand how the material evolves around multiple stars. And we know that disks form. So what we need to do is study disks in multiple stellar regions, multiple stellar systems. So the strategy here is to do surveys of star-forming regions, and then what we're trying to see if where are the disks, are they frequent, are they different from single star disks? Is there any evolutionary trend hidden behind this? And the observables we use in this case are the flux, the orbital architecture we can observe, the disk stellar mass ratio, the disk size, and its structure. So here I'm showing, there are many surveys in the last years. I'm just showing one example here by Carlo Manara and collaborators, where you can see several disks. So here you have mainly binaries and one triple that we can see there, UZ tau. And what we can see is that we have information of the gas disk and the dust disk, and we can compare the size there. And there is this very interesting result that it's an IMPREP work by Alessia Rota, where they basically comparing the radius of the gas and the radius in the dust. And you see that it's basically twice or 3 times larger in the gas compared to the dust. And this is really interesting because one would expect that tidal truncation would put that closer to 1, but instead we see something very close to what happens around single stars. Well, we can also do another approach that was followed here by Rachel Atkinson in 2019, where you basically plot the cumulative probability as a function, sorry, the flux as a function. So you have the cumulative probability of the flux, let's say that this way. And what we see is that there is a disk penalty assigned for multiple systems in the sense that you receive less flux from these disks. And this is interesting because it means that there is less material, or perhaps that they live less in terms of in time. Another thing that we can see is the mass ratio between the disk and the star. And we see that regardless you are the primary or the secondary, you more or less get the same ratios, which is something, again, a bit surprising because one might think that different mass ratios between the star would impact the amount of material around. And another thing is that separation here matters. If you're a very wide binary, that changes a little bit the trends I just showed. And if you're a very, let's say, very short, a very tiny binary, that will heavily truncate the disks, so it's going to be very hard to detect. Okay, and if we go to the other end, we also know that binaries host planets. So this is very interesting because it means that these disks that we just showed should form planets, and they do. So here, if we take the simplest multiple system we can think of, which is a binary, we can have circumbinary planets which are of P type or S type. So the former are the ones that orbit around the center of mass of the system, of the binary, and S-type planets orbit around each of the single stars. And here I'm showing a figure from Martin 2018, where you see the planet semi-major axis and the binary semi-major axis. The takeaway message here is that we have thousands of exoplanets, but we only have a bunch, a few, or let's say a few dozens of circumbinary planets. And so this is due to biases effects, but the important takeaway message here is that planets do form, and they form where we expect them to appear, because you have some regions of stability, of instability, and those seem to be depleted. So things are coming together here. And there are two very nice reviews that I want to point out, about the formation and evolution and the frequency of circumbinary planets here. And I would like to remind you that Proxima b is part of a multiple stellar system itself, which is something that is, again, we need to think about this more often. And my point here is there is an emerging circumbinary planetary population, and also the takeaway message is that planet formation seems to be very resilient in this case. So multiplicity has often been seen as a problem historically, because when you have a star in the field messing around, you get dirty signal. So it's better if you remove them to have a clean signal in radial velocity surveys, for example. Regarding transits, transits are less likely if you have a multiple system, but they're a bit more free of this bias that I was just mentioning. Regarding high contrast imaging, having another star in the field is quite annoying, especially if you're doing adaptive optics. So again, this is a problem to have multiple stars, and they tend to be left out of the samples. But now there is the companion, there is an active search of companions in disks and also around planet hosting stars. And I would like to point this program Destinies by Ginsky and collaborators done with Sphere, where they're pushing and they're using the imaging techniques at the very limit. And they're finding some companions where people thought that before there was nothing. And that might explain a few things. Another important aspect that was observed is that disk lifetimes seem to be shorter because, I mean, you're having a very dynamical interaction with the companion. And something which is important to remember is that no detection does not mean no binary, but because you could have a disk which has evolved as a binary, but you're not detecting the companion because it's low mass or it's hidden perhaps in a cavity. But fortunately, we can put some upper limits. And if you want to know more, I invite you to see the talk by Jorquera. And here we know that in the last 5 years, the community has actively chased multiples, and there are some very nice examples. So it's not a problem after all. But it's a problem for theorists. Why? Because you want to understand the evolution of disks and binaries. That's important because the fact that you have two stars is messing around the classical picture we have. So circumbinary disks tend to be truncated from inside, and they are highly perturbed by torques, as we will see in a bit. And another important thing is that circumstellar disks are heavily truncated and probably very short-lived, according to the orbital parameters we consider. So this means a very interesting thing, that planet formation needs to occur even faster in these systems if we want to form planets. Another problem is about dust dynamics and growth. One may ask, how do I retain the solids in the disk if I have such a steep gas disk which is being truncated from outside or from inside? So it's a problem that has been tackled. You can go and see the poster by Francesco Zagaria. And there is also the problem of growth. If you excite your disk in such a way that the relative velocity among grains when they collide is over a certain threshold called the fragmentation velocity, then you destroy the little solid bodies, so you do not form planetesimals. So there is a talk by Belén Blanes on this. And one of the solutions might be to form traps within the disk that would stop the dust from drifting and make it grow by keeping the relative velocity low. And then on the other end, we want to understand, so multiplicity is also a problem if you want to understand the planetary architectures we can have around the multiple stellar systems, because there are some forbidden, so let's say chaotic regions, versus stable regions where you might find planets. But these planets are very hard to observe through surveys, transit surveys, for example. And one of the nice conclusions that came in the last years, mainly thanks to the work of people doing celestial mechanics, is that giantess planets should end up very close to their star. If so they're orbiting around one of the stars, and they migrate very efficiently. And that could explain partially the population we're observing. So we need to keep in mind that we have these problems at the moment, but planets still form. So again, planet formation is resilient in multiple systems. And one would like to understand what's the impact from one end to the other, from class 0 to main sequence, because multiplicity seems unavoidable and ubiquitous. So if one comes to this question: if all stars are if all stars are born multiple, what don't we see multiples all over the place? And so in order to solve this, we need to understand from the observational point of view what signatures should we search in disks, and on the other hand, for theorists, we need to understand this evolution that I just mentioned. So now let's go to the part 2, where we're gonna see a little bit what kind of disks we can have in these systems. Let's start with the easy picture. So we have the scenario number 1, 1 star and 1 disk. In this case, we have 1 spinning star with material around. And what we have is a disk. We can have rings, we can have warps, jets, outflows, and a cavity. And this is in very good agreement with the picture of the solar nebula model proposed by Xu et al. In the 80s. So this is the view. You have a rotating star, you have outflows, you have a very nice disk edge on. And but if we now look at this face-on view, this is what you might see. So you see a very nice disk with structure, which is mainly axisymmetric. And we know that the disk spreads outwards due to viscosity, and that after a few million years, a cavity is carved in the inner parts due to winds and photoevaporation. So here you have 2 prototypical cases, HH30 and AS209, that are like this. So perhaps you are more used to see HH30 like this without the outflow below, because it's a monopolar outflow. It's a fascinating system. In the following, the disclaimer is that for simplicity and to avoid making my life miserable, as Didier Queloz advised, I will not consider magnetic fields, nor winds, or stellar tides. Okay. Well, now in the scenario number 2, we have a binary, so 2 stars and several disks. I was almost shocked when I saw this picture by Dali, this drawing, which I think is fantastic, because you can see that there are 2 dancers. So this is analogy with the dance that are orbiting around each other. Each of these dancers has an own disk, and you have an outer disk which seems to be, so in this case it's the dress, which seems to be eccentric, and you have these flows, and this is a wonderful drawing in my opinion. Dali would have been a great astrophysicist, I think. So what we have here is 1 circumbinary disk in the outer parts. We have 2 circumstellar disks, and we see that the binary here, it's the source of asymmetry, and this leaves very characteristic features, as we're going to see in a bit. So if we zoom in, this is what we're dealing with. We have 2 stars, and there is some material that could be around each of the stars blocking the star. We're going to see that has important implications as well. So these cavities have been actively studied in the last years, but this study really began in the 90s with this seminal work by Artimovitz and Lubov, where they basically studied the way material flows inside the cavity, while you have at the same time gravity, or also the binary torques pushing material outwards and avoiding material to fall. And so this is fascinating, because they found more or less that the size of the cavity should be 2 or 3 times the semi-major axis of the binary, and that the disk should remain basically circular. But now, with the computational capabilities that we have now, there are many people working on this, following a very careful numerical approach, but it's a very degenerate problem, because we have many parameters. So we have the mass ratio between the stars, we have the semi-major axis, the eccentricity, and also the inclination. And another difficulty comes here, because we have to consider 3 different timescales. So there is the dynamical timescale, which is basically proportional to the orbital timescale of the binary. We have the secular timescale, which is of the order of 100 or 1,000 binary orbits. And then we have the viscous timescale, which is sometimes even longer. And so, as I said, there are a lot of works regarding how cavities should be shaped and how large they should be. And so here I'm showing an example below. So you can see here an example of simulation done with SPH by Kiran Hirsch, published this year. And you can see that changing eccentricity and the mass ratio, you do have very different cavities. And you can also play with the inclination, as he did. And something which is interesting is that you can compare grid versus SPH or Lagrangian methods, and they seem to disagree a little bit regarding how eccentric the cavity eventually gets, and how this cavity starts to precess around. But there are also nice results showing that by doing so, we can create traps, and these traps avoid dust falling onto the star. So we might be solving this problem, but it's still a matter of discussion. Then if we go to misaligned binaries, we can ask, do we see misaligned binaries with respect to the circumbinary disk or not? And here I'm showing a plot produced by Jan Sekala last year, where he basically found that there is a correlation between the eccentricity, so here the angle, so this is the relative misalignment as a function of the orbit of the binary. So we see that very short binaries, so when binaries are very close, so the stars are very close to each other, so you can see also here with the semi-major axis, the misalignment is very close to zero, so alignment, perfect alignment. But when you get binaries that are larger than 1 AU in semi-major axis, then you start to see some spread, and you see that misalignment seems to be the rule, and alignment is not anymore what you should expect. And there is also a poster in this conference by Jensen, when he finds that circumstellar disks have a tendency also for alignment in binary systems. Then another very interesting phenomenon that was studied in the last years is the disk breaking or tearing phenomenon, where you basically have that the star, the binary inside the cavity, is the torque dominates over the viscous torque of the disk that wants to keep the disk aligned. And under some conditions, you can break the disk and this inner disk starts precessing. So this is something that was studied by Nixon and Facchini and collaborators. And here I'm running a quick hydrodynamical experiment where you put a misaligned inner binary by 60 degrees with respect to the circumbinary disk. You let this evolve, and you see that after a few hundred orbits, the disk is broken, and you have that the inner disk, highly misaligned, starts to precess inside the cavity. And this has very interesting observational consequences, because you can have moving shadows because you're blocking the light and then you're moving the disk that's blocking the light. And it gets even better, because if now we allow the inner binary to get eccentric, in that case, we have another phenomenon, which is polar alignment. And in this case, as I will show in a bit, we can have a binary which is orthogonal with the inner disk. So the requirement for this to happen is that you need the initial eccentricity or relative misalignment, sorry, the initial inclination or relative misalignment to be larger than, well, let's say that 40 or 30 degrees. And you need the eccentricity to be larger than zero. So this was first studied by Ali, the collaborators, and also Martin and Lubov, and there are several works on this. So if we run the same experiment now by putting an eccentric binary, you can see now the video here that things do not happen the same way as before. Now we have that the disk is slowly breaking, and when it breaks, so now you can see that there are two disconnected disks in there. The broken component, so the inner disk, is not moving at all, it's fixed, and it's orthogonal to the inner binary, which is at 60 degrees. So this is great, because in this case, we do not have moving shadows, and we can disentangle. So in a way, you could measure the eccentricity of the binary that you cannot see, because you see that the shadows are not moving. And if you're interested in dust dynamics and also in misaligned disks, there are a lot of talks in this conference by Ali, Gonzalez, Poon, Poblete, Balabio, and there is also a poster by Cristiano Longarini. Moving on, if we now go to higher order, let's put 3 stars and see how many disks we can get. In this case, if we have a hierarchical triple system, which means that I will talk about this in a second, but if we have a hierarchical triple system, basically what you have is that the semi-major axis of the inner binary is much smaller than the semi-major axis that you have between the tertiary and the center of mass of that inner binary, as shown in the picture here. So the inner So the semi-major axis here is much smaller than the semi-major axis here. If this happens, the maximum number of disks you can have is 5. You have a circumtertiary disk here, then we have a circumbinary disk here, and we have potentially up to 3 circumstellar disks. And in this case, things are even more complex because you have many different effects acting all at the same time. We have warping, we have disk breaking, we can have precession, we can have libration. And this has fascinating observation features such as shadows, wingling jets, and things that we're going to see in a bit. And one thing that I'd like to emphasize is that these highly misaligned systems could easily be formed through accretion. And there is also this idea that disks might form, you have these second generation disks. And if you want to learn more about this, I invite you to see the talk by Kufmeyer in this conference. So if we want to understand triples, one needs to follow their evolution since when they form and see how they end up. And this is an experiment, a numerical experiment that Repurth and Nicola did in 2015, where you can see that you have 3 stars, and there is material around. And according to how you accrete material, you can end up in different places. And this is what they obtained. So they start with random orbits, and most of them have hierarchical decay, which leads to stable configurations. And when they extract the stable configurations from their sample, this is what they get. So they start here, basically, where you have equal mass, an equal mass triple, because this is the mass ratio between the tertiary and the total mass, and this is the mass ratio of the inner binary. So here means all the stars have the same mass. So they throw all the simulations and they see that you have a stable region here and a stable region here, which means that there are a lot of things that decay and there are some stable systems that we should expect to observe in the field. And indeed, we observe hierarchical configurations in the field because they're the most likely to be found. And I would like to know that if we have large separations, then that means that we will have very long periods, which means that it's very hard to constrain the orbits on an astronomer lifetime. And because most of the time, if you have a very eccentric and a very large semi-major axis, you spend most of the time at the apocenter. Another interesting thing is that these highly misaligned configurations can be inferred by the disk geometry, jets, outflow, planets. And when you see such strange structure, this could be caused by companions. And this is something that there is a talk by Murphy that discusses this. And on the other end, when you look to the planets, there are some weird hot Jupiters and sub-Neptunes. And I would like to highlight one system in particular, HZ 3167, where you have 3 coplanar sub-Neptunes, so 3 planets which are aligned among themselves, which are polar with respect to the rotation axis of the star. This is very surprising. And so this is just to let you to show that misalignment is very often found in exoplanetary systems, and we need to understand them properly. Last point, if we have hierarchical ejection of stars, that means that there should be some hints in the stellar kinematics and clustering that we have in star-forming regions, and that leads to the idea of free-floating stars. And this, we're going to discuss this in a bit, could be a source of flybys in regions of low stellar density. So the question here is that if you eject a star with material around and then you form a planet, do you keep a memory of your natal environment or not? That's something to think about. And before going to real systems observed, we can also have multiples undercover. And this is the binary paradox, as Fermi would have called it. Where are all the binaries? If everything's multiple, where are the binaries? So perhaps we're missing some or a lot of them, but perhaps some are not multiple anymore, but they used to be multiple, as I just showed. So in this case, what we want is to hide substellar companions or stellar companions within the cavities at AU distances, so they can remain below the radar or behind the coronagraph, but they still have dynamical signatures on their circumbinary disk. So we're going to see a few examples in a bit, but basically, if you see this kind of structure and you see only one star, it's likely that there is a companion in there, perhaps not of stellar mass, but of planetary mass, which is shaking the disk and creating all these strange features. But one needs to be careful because disk structure can be a bit treacherous in the sense that if you perform very aggressive ADI, some arc-like features might become point-like features. So to avoid this, you need several independent observations and to combine several methods to get rid of this. And there are some lessons to be learned from Leak Calcium 15, and there are 3 talks at least on this source. I invite you to see them. Alice just discussed this system as well. Okay, now part 3. Let's start this multiple tour. So this is going to be all the systems we're going to see. There are a lot, and they're fascinating. And thanks to all the contributed talks that were online. I really enjoyed watching them. The disclaimer here is this is a conference selection bias here. And I tried to pick the representative systems of a class. And sorry if your favorite system is not here, please bring it up in Slack and let's talk about it. Now buckle up because we're gonna go a bit fast now. The first system is HD 142527, which is circumbinary, not transitional disk. So here, this is a well-known example. We have structures, we have shadows, we have a dusty banana, we have accretion flows in the cavity, and many, many more things. And this system was actively studied by Casasus, Avenhaus, Marino, and collaborators in the last years. And since there was so much structure, there was this idea about that perhaps there is an inner companion in there, proposed by Fukagawa in 2006. And actually, Biller and collaborators found that little guy in there. And so by then measuring its movement inside the cavity, you can have an idea of the orbit. And this is what was done by Lacour and collaborators, and also by Claudi a bit later. And what you can see is that with this very small arc, you can try to guess what's the orbit of this little companion in the cavity. And basically, the takeaway message here is that there were 2 families, one red and one blue. So with Daniel Price, we said, okay, can we say something about this? So we did hydro modeling of this. And basically, we saw that the orbit of the inner companion was very, very closely related to the morphology that was created in the disk. And in particular, you can see that there are accretion flows. There is an inclined inner disk that might be casting the shadows that Avenhaus reported here and that Marino and collaborators said that was caused by inclined inner disk. The inner disk is there, and you form it easily for red orbits at least. So there are more information about this system in talk by Daniel Price, and there is also talk by Garg describing morphology in this system. And there is an active ongoing discussion in the community about AB Origa because is there a golden binary there? Because we have observations with sphere which are wonderful, and observation with ALMA as well that show that there are spirals in there. And this is a clear hint that something's messing around in the cavity, but we still don't know if that's of a planetary or stellar nature. And I invite you to see the talks by Poblete, Curry, and Pablo Riviere if you want to know more. Now, moving on, HD 10453, precession inception. So here, there are a couple of talks, the first by Jeff Gonzalez, where basically what you have here is that you have one central star and there's an outer companion. And again, we only have a small arc of this outer companion. And we can try to model the orbit and try to guess what's the, not guess, like we can compute what's the more likely orbit for this. And what we found is that the orbit is eccentric and it's also inclined, which is very interesting because this leaves imprints on the morphology and the kinematics of the disk that are discussed by Jeff in his talk. But then what is the origin of the inner cavity? And also what's the impact of the misaligned companion on the evolution of this system? So I went to see Beck, and Beck said, oh, easy, I'm quoting her, actually, easy peasy lemon squeezy, let's just put a planet in there. And indeed, we can put a planet which generates a cavity. It's also very nice because it disconnects the inner disk with the outer disk here. And what you have is that you can put upper limits on the mass of the planet, because otherwise you should have seen it. And we have a long-lived nested precession, which is called precession inception. So if you want to know more about this, I invite you to see her talk. Now there is another system, HD 143006, where you have disk breaking and precession in action. So this was first observed by Miriam Benisti and collaborators in 2018. They discovered a lot of very intriguing structure in this disk, and in particular this shadow here that was very hard to explain. But they used the model by Stefano Facchini and collaborators, where you basically break the disk and you cast this shadow with a disk which is not completely orthogonal, it's just mildly misaligned. And the problem is that these models were for Q = 1, which so equal mass binary, but the observations put some constraint on the mass of the binary that should be there to generate this structure. So Giulia Benabbio went a step further and she put a binary there with a planet as well. And so here I'm showing the gas and the dust in here. And you can see that doing radiative transfer simulations, calculations, we recover a very good agreement. So if you're interested on dust in these systems, I invite you to see these talks by Ali and Longarini. Then we go to the polar circumbinary disk. It's a fascinating system. We have 4 stars. And the disk around this little guy here is actually polar. So it's orthogonal with the binary plane here. And you have this outer binary going around. So again, this was expected from the theoretical point of view, but it was the very first detection. So this was very exciting. And one can think about, can we form planets in here? And if we do, we can then ask the following question: are these planets stable? So the answer is yes, but we need to be careful about the outer perturber here, because once the gas will be dissipated, the planets that might be there as leftovers planet formation should become unstable, as shown by Jupone, for example. And there's also a work by Chen and collaborators where they study the stability of such planets. GW Orionis, a wonderful system. This is my favorite system. It's a wonderful laboratory. You have everything you dream of. It's a hierarchical triple stellar system with disk tearing and precession in action. And you have so the inner binary with a short period and the tertiary with a period of 11 years, and it's eccentric. This is important. And in here we have a circumtertiary disk here, and we have a circumbinary disk here, and you have warps, shadows. It's a fascinating system. And also the stars seems to be, the star orbit seems to be misaligned with respect to the circumtertiary disk, which is something, again, landing support on this misalignment scenario, that everything is misaligned, basically. And if you want to know more, there are a couple of papers here and a talk by Stefan Kraus. Moving on, I'm going to go fast now. We have GG Tau and T Tauri, which are classical triples. So here you have a cavity and you have 3 stars inside the cavity. And so this was observed with a sphere. And you can see that there is a lot of structure. It's a huge mess, but it's wonderful. On the right, you have the most famous T Tauri star that actually gave the name to a class of stars that is itself a triple star with disks and some nebulosity around. And this is the model that Beck and collaborators came up with. So you have this circumbinary disk with outflows, and you have another outflow here, a disk in here. It's just wonderful. And in these cases, I want to highlight that triplicity definitely plays a role in here. Now, there are 2 triple stellar systems in the D-Sharp survey. These were studied by Nicolas Kurtovich. And so we have HT loop AB. If we zoom out, we see that there is another guy in there in the field. If we zoom in, we see that there are wonderful kinematics there that tell us a lot about what's happening there. And again, the gas disk, so here I'm showing the moment 0 of CO. The gas disks seem to be larger than the dust disk as expected. The other system, the other system is AS205. So here again, we have, so here there is 1 star, and this is actually a binary. And we do see that there is a lot of material around, again, CO moment 0 map. So this is the moment 1 map. So I don't have time to go into detail, but please read the paper. It's fascinating. And so here you have a lot of material, and there is a hint of a bridge between the 2 stars. And actually, We observed this with Seba Perez and collaborators, and this is the image. And you can see that, again, we recover all this structure, and it's fascinating. We think that this might be, again, a flyby, but this is work in progress. Oh, sorry, this is Andrew's 2018. And here you have, again, the kinematics, which is fascinating and give us a lot of information about what's going on there. Now, one of my favorite sources, again, X-Tauri. This is a quadruple stellar system. So you have a binary in here, primary here, and a perturber here. So we talk about a flyby when we have a stellar encounter between two or more stars. And this has been actively studied in the last years. Prograde encounters are much more destructive than retrograde, for example. And there is a lot of work about the morphology that is created during these encounters. And this idea is often controversial because it's unlikely to have these encounters. In fact, you need very crowded stellar environments for this to happen. Yet we do see some flybys, or at least we think so. There is RV Auriga, HV Dotau, and X-Tauri, the one I'm showing here. And so we observed this source with sphere, and pushing the instrument and the signal to no acceleration at the very limit, we get these wonderful spirals that are recovered. So this is the scatter light image obtained with sphere, and this is a modeling what we did. So this is the gas distribution during a prograde encounter where the star comes like this and generates these two beautiful spirals. So there are other scenarios that could explain this. For example, a very eccentric binary that comes once every, let's say, 100,000 years, or late info from the envelope. And one way to solve the likelihood problem is that by saying that there is some structure in stellar clusters, even in regions of low stellar density. So this is something that, for example, was shown by Isabelle Roncourt a couple of years ago. And again, kinematics give us a lot of information about what's going on there, and we can reconstruct the whole thing. Now, moving even faster, if we go to class 0 and 1 objects, we can actually see systems caught in the act of forming multiples. Here, just two quick examples, one by Tobin et al., one by Alves. This little guy here was called Cosmic Pretzel, which I really like this name. And there is this wonderful survey called Van Damme, which likely will be discussed tomorrow about these kind of objects. Then there is this other fascinating object. So this is crazy. You have a circumbinary disk and two circumstellar disks. You have jets, outflows. There are 3 talks on this in this source. Please go and check them out. Check them because it's crazy what's going on here. And we have, again, very nice kinematics that allow to understand what's going on here. Then we have IRA's phone number. Here again, we have a very young system, which is triple. And this system is actively accreting material. And we can see that there is some misalignment between these two disks and the circumbinary material here. And again, we have kinematics, and it's even better because you can also have an idea of the orbit of A1 around A2. So please go and check these talks by Moreira and Oya if you want to know more. And the last system I want to discuss is this one, which is a little cousin of HL Tau. And it's a system located here. It's a binary. And if you go and look the disk around B, you see that it's very compact. It's perhaps the smallest disk ever observed. But there is, again, a poster by González Ruilova where perhaps there is a disk even smaller. And these dwarf disks have, I mean, they're very interesting, although they're hard to detect, because they might be precursors of compact planetary systems. And in these systems, the dynamical evolution needs to be even faster. And there's a talk here by Osorio. So coming to the conclusions. Where are we 5 years after HL Tau? Well, we know that ALMA and high contrast imaging have produced groundbreaking discoveries. We know now that spirals, shadows, warps, rings, gaps, accretion flows, jets are the rule rather than the exception now. We're not surprised anymore when we see this. And there is a clear synergy between communities. So we have the observers that produce exquisite data and the theories that are being very imaginative, throwing crazy ideas. And one very important thing is that we're combining a lot of observations. So this multi-wavelength approach is key to have this 3D reconstruction of the disk. And we're gaining grasp on the dynamics, but multiples remain strange beasts, as was designed here, sketched here by Escher, this is the way he sees stars, or he saw stars. And we're also realizing that there is a lot of, the environment plays a major role here in terms of tidal location and external photoevaporation, and also that in setting the initial conditions for disk formation and evolution. And there are two talks about this, one by Hugo Lebreuil and one by Kufmeyer again. And these conditions are key to understand the planetary architecture and the stability and the composition of the planets that form. And most likely Gaia will unlock a lot of things by understanding a little bit better the gaseous filaments where stars form. And there was a workshop in November about this, and there is online material if you want to check out. And before we leave, some cavity questions. We need to understand how cavities behave across classes. That's a main important point. Then how does late accretion affect the cavity morphology and the accretion on the stars? And there is also the problem about dust growth in circumbinary disk and circumstellar disks. This competition between destruction and trapping and growth that we need to understand better. And disk in multiple, we know that they live fast and they die young. So perhaps this is the role of self-gravity for young stellar objects that plays a major role in forming planetesimals. It needs to be further investigated. And finally, there is a missing link between multiples and the accretion phenomena from the disk to the magnetosphere that will likely be studied in the next years. And if you have more questions, please put them in Slack. It would be nice to have a nice discussion on this. And before I leave, I want to advertise that with NGVLA, we're going to unlock the AU scale, and we're going to be able to see variability on the order of 1 year or even less. So here I'm showing results by Harter et al., where they put a super Earth at a few AU, and they do see some variability, and they can recover a very nice structure with the NGVLA. So these are predictions. And there's going to be a review talk tomorrow on this. And the avenues for the future. So we have an emerging population of disks and planets in multiple stellar systems, all the way from class 0 to the main sequence. Gas and dust dynamics can be done now with chemistry. So this is the way to go, I think, now. And we are, I want to emphasize that kinematic era has already begun. And there are two very nice talks by Christoph Panta and Giuseppe Lodato. And there are many more multiple systems in the way for in the next year. So we need to do some predictions and think about where and what should we search in these systems. And finally, we need to understand what's the planetary architecture in multiples, because when you talk to dynamicists, they know that there is a lot of information encoded in the orbits, and you can recover what happened during the disk phase. And this is a very exciting moment to do this, because we have many fields intertwined. We have star formation, disk dynamics, stellar evolution, planet-disk interaction, celestial mechanics, all these things coming together. And so I was very happy to prepare this review talk for you, and I will take questions. Thank you very much for your attention, and let's chat.
Hi, Nicolas. So thank you very much for a very nice review and showing us all the different, the zoo of this that we can get in binary systems. So I think we have a poll here. So the question was, if stellar multiplicity is ubiquitous and we mainly see single stars, where are the missing multiples?
Yes, it would be nice to see what
we have a few answers yet. So let's wait a little bit to see for people to respond.
Well, it seems like hierarchical decay, it's most likely. I'm happy with that answer.
Okay, so you agree with that?
Yes, I think hierarchical decay is the main source. But again, as I emphasized, some of the single stars we're seeing were part of multiple stellar systems before. And that might explain some of the anomalies we're seeing when we compare to single stellar systems. So yes, I agree. I totally agree with it. But I also think that there are some hidden binaries that we cannot see that remain under the radar. So yes, I think the two more likely here are in my opinion, the right answers to this question.
And what about the other ones, the very wide binaries or just?
Well, very wide binaries is something that is very hard to tackle because, again, as I said, it's very hard to know that these stellar objects are bound or not bound. You can think in terms of survey, if they're co-moving, perhaps there is a hint in there, but you also have a lot of stars which are co-moving in stellar environments which are not necessarily bound to each other. So it's a hard question to tackle observationally.
But I guess that Gaia will help a lot there.
Yes. Gaia Data Release 3 is going to be excellent for this because we're going to understand much better how stars, I mean, the kinematic structure of filaments and how stars are bound to each other in those regions, which are regions of particular interest when we think about external photoevaporation and tidal encounters and these things. So yes, Gaia is going to be very helpful in that regard.
Okay, so let's go to Slido to see the questions. We have a lot of questions. So there are questions about theory and about observations. So I guess we can start with some of the theory questions. So what causes a binary disk to be misaligned with the binary in the first place? So what are the...
So this is one of the common criticisms that one might have with the models that start with already a misaligned disk and then we see what happens. And there are many interesting things that happen, of course. The answer to this is if you go back to Matthew Bates' simulations and people working on how material is distributed around young stellar systems, you do see that misalignment seems to be the rule rather than aligned. There is no, in other words, there is no preference for alignment at the very beginning. Then, of course, if you let the system evolve, there are basically two stable configurations. One is coplanar and one is polar. But at the very beginning, the time it takes to realign, everything is misaligned. So if you start with something which is highly misaligned and probably eccentric binaries or triples or whatever, things are going to get wild. And that motivates the initial condition we use as modelers.
Okay, so there is a question about radial drift. Is radial drift different in disk around single stars and multiple systems? I guess it means the radial drift of solids, right?
Yes, radial drift of solids. So when you have a binary, as I said before, you can truncate disks. The gas disk is a bit larger than the dust disk. The problem here, there is a poster about this by Francesco Zagaria. But basically, if you have a steeper radial profile, surface density profile for the gas disk, then you will have a faster radial drift and you will lose your material onto the star much faster compared to a single star where things are less wild. So that's the short answer.
And are the observations consistent with that? Do we have observations to...
So this is an ongoing work. Yes. So we do see that there is continuum emission coming from circumstellar disk in binaries. So material is not lost. And we also have planets around these guys. So you should form planets, material should stay there. The problem is that if you take radial drift models, yes, we do have material flowing onto the star, but the surveys, for example, the one by Carlo Manara, shows that there is a difference in size, but there is continuum emission, so there is millimetric dust in these systems.
Okay, so another theory question, is a circumbinary disk the only possibility in a triple system? Could you have a stable configuration where each star is surrounded by individual disks? I think you mentioned this a little bit, but...
Yes, so in a so if we have a triple star, which I will suppose for simplicity that it's in a hierarchical configuration, as I explained, it's unlikely to have two circumbinary disks because the way stars move avoid that kind of disk. So you can have at most one circumbinary disk, but for sure you can have circumstellar disks. I must say that there are not many studies that tackling the stability of particles like through n-body simulations or even hydrodynamic simulations, stability or the way this circumstellar disk in triple stellar system might form. But there are, as I showed, there are very young systems where you can see 3 stars with a lot of emission around each of the stars and material all over the place. So these things exist.
Yeah, there are some ALMA detections around, very compact disks around each one of the components in the triple systems. I don't know if they are very common, but I have seen some.
Mm-hmm.
Okay, so I guess we can go to some of the observational questions. One is about the multiplicity surveys in class 0 and class 1. So how complete are these surveys, and also if they have the same IMF of the class 2 sources, right? Because we know that multiplicity is also a function of a stellar mass. So the question is whether we are comparing apples to apples when we compare the multiplicity of embedded sources versus class 2 sources.
Yes, so I think this is something we should discuss tomorrow, probably. I'm not sure, I don't have the answer, to be honest. I think the fact that you have multiple systems that not drastically change the IMF. Regarding the completeness of these surveys, I must say I wouldn't know how to assess how complete these surveys are, but Van Damme has done an incredible work in searching for multiples, and so perhaps we can discuss this tomorrow,
Okay.
I guess.
Yeah, because I guess the worry there is some observational bias that you might have with respect to the mass. Okay, so another kind of observational question, which is the binary separation beyond which the millimeter fluxes and these sizes are the same as in single stars, right, in single systems. I mean, what is kind of the smallest separation you need for a binary to actually affect these properties?
Well, the thing is that the disk, the circumstellar disk, I will assume that the question is about a circumstellar disk and a binary, which is the companion which is outside, and the question is about.
No, I think it's about the properties of the individual disk. Right?
Yes.
Yes, individual
So
disk.
the fact that you have an outer companion heavily truncates the disk at the very beginning. So I don't think there is a clear criteria to say below this limit you will be very different. One could think, of course, about if I put something close enough, I would have a very small disk, which will be very short-lived. And then that means that it's unlikely to observe those disks, of course. But again, I would like to point out what I said at the very beginning, that when you do surveys of multiple disks in the continuum with ALMA, for example, the flux coming from the circumstellar disk in binaries is smaller than the one from the single stars. So that makes them harder to detect, I think.
Okay. Yeah. So so there are some recent results by Zurlo et al. That you can also check. I think it seems that the critical separation seems to be about 100 AU. So I don't know if that's what you expect also from the models.
Well, I think that you can put whatever you want there. Then the problem is how long the disk should live and how would the dust evolve in there. But we do have examples like HD 100-453 where the separation is less than that. It's 50 or 60. And we do see structure in the dust. We see in the continuum. We see a lot of structure in there. So I'm not totally sure it's a good idea to talk about. I will read that paper carefully, but I'm not sure we have a clear criteria in terms of semi-major axis to put in there.
Of course, I mean, it's going to be a kind of a distribution.
You can scale things up and down, and it works pretty well from the modeling point of view.
Okay. So there is a question I think you have already answered a little bit. It is possible that stars with high accretion rate and large gaps are actually circumbinary systems. So you show that that's possible, that you show several examples. So the question is whether you have a feeling of how common these systems are, right? And what fraction perhaps of these systems that have large cavities and high accretion rates are these uncovered binary multiples? Yeah,
so I think again there is a biased effect hidden in here because, for example, Antonio Garuffi did a sort of classification of the sources we're seeing with sphere and ALMA. and we're seeing the very bright guys with large cavities. And I guess in that category, in particular category, yes, some of the transition disks that we are seeing might be circumbinary disks. Then if we think about the very small disks that we should expect for all the other stars, which are more numerous, let's say, I don't know if we can apply that to that. But if that's true, it means that there are a lot of very small separation binaries. But again, this is something that we're a bit limited observationally speaking, and models are a bit, you can scale things up and down and it works fairly well. So I wouldn't know for very small and faint objects.
Okay, so I guess we need more radial velocity observations, more aperture masking observations, interferometric observations to go to the very close binaries.
Well, there is a very nice discussion ongoing about AB Origa in particular, and perhaps the data release 3 of Gaia will allow us to understand if the star in there is wobbling or not, or at least to put constraints, very strong constraints about what kind of binary you can put in there.
Okay, so thank you very much. I think that's all the time we have. So we can move the rest of the questions to Slack and the discussion. And also remember that we have a lot of posters and talks for all the topics for this particular session too. So I encourage everybody to take also a look to those additional talks and posters. And I thank all the speakers again, and I think we go back to Antonio now. Thank you very much.
Thanks, Lucas. Yes, just to wrap up the day, and thanks all the speakers for the excellent review talks we hear today, and thanks to you, Lucas, for orchestrating so well the discussion and the Q&As. So we'll reconvene tomorrow for the last session of this conference. Have a good day.